Designing a Mars colony for long-term use in scientific discovery requires that we refer to mission objectives, environmental factors, basic human needs, and survival versatility for design cues. Duell puts it well in his paper that colony design has to be perceived as a scientific experiment performed by an architect. The process of design requires that architects and designers examine all the parameters, specifications, and boundaries of a project to determine what form the building takes. A habitat must allow for every aspect of life for the humans living in it, so an architect's design for a Martian colony must consider almost every specification involved with the mission. The Martian environment, although better than the Moon, is unforgiving to humans. We need protection from extreme temperatures, low air pressure, harmful radiation, Martian dust storms, and possible biological contaminants. Several precautions must be taken to make a livable building on the surface. A habitat will essentially be its own ecosystem, being tightly sealed off from the Martian environment. Materials will have to withstand extreme cold and remain strong and flexible and not brittle. The exteriors will also have to provide radiation shielding in special safe zones, as Martian atmosphere protection is spotty and seasonal. This could be achieved with reflective painting or with a composite plating, like a double-pane glass with water in between. The permeating dust of Martian atmosphere will have to be strictly regulated from getting inside the habitat, as could affect experiments, the function of machinery, and poses a dangerous health risk to astronauts. It is unknown what chemicals could be included in the dust, but there is potential for chromium-6, cadmium, or arsenic, all of which poison the body and can cause cancer. Any habitat entrances could require decontamination systems to prevent dangerous chemical and possible biological particles from entering or exiting the habitat, as well as airlocks to maintain pressure inside. Quarantine rooms could also help prevent the spread of unknown Martian diseases, as well as any disease brought from Earth. The interior environment will be designed as well. The building needs life support, physical and psychological. The physical entails oxygen, water, and food. There will be life support systems included, such as atmosphere recycling and water reclamation. Possibilities include separating carbon dioxide into water and oxygen and carbon monoxide, mining for water and permafrost, and more interesting will be the psychological support. Hydroponics, knowledge of being the farthest away from Earth than anyone ever before, on another planet no less, will contribute to high stress levels in our astronauts. Studies show that when relocated, people try to form personal attachments to the new place in order to form a more solid personal identity. People also need social interaction to establish their place within a community. To facilitate belonging with others and on Mars, daily activities must revolve around community gatherings and daily work. These psychological needs on a longer Mars mission would entail large gathering places for meals and events, places of worship for religious colonists, areas that allow for introspection and self-examination, as well as safe areas for psychological examination. The design should consider making each area of the habitat as unique as possible to allow colonists to form attachments with the building. Mission parameters must be supported by the colony. It's the whole purpose of being there in the first place. Several mission plans share similar objectives: searching for signs of life, signs of water, determining the habitability of Mars, exploring the areology and history exposed by it, as well as other scientific exploits. The landing site will have to be near the anomalies to be studied, so the specific point will be tailor-picked to facilitate all of these goals. A selection process will look for areas with potential water and permafrost, areological anomalies, and volcanic areas to land near. The colony would facilitate exploration and study with multiple workshops and laboratories for examining chemical, biological, and aerological samples. To do field work, scientists would need a ready supply of EVA suits and rovers, so plenty of supply rooms and repair rooms as well. Other features of interest could include a scientific greenhouse for study purposes. Most importantly, the colony will need to be versatile to adapt and react to changing situations. A maximum amount of redundancies will be built in, and the security measures will be taken. The colony will need to produce, create, and manufacture many of its own products. If new tools are needed, it would need to make them. If new protection must be created, it would have to use material around the base. The colony must facilitate ingenuity and manufacture for survival. One example could be a robotic arm that could 3D print in multiple materials so they could build anything. Mobility is also needed when the going gets too tough for the colony. The site could become unstable due to unseen circumstances, so relocating is necessary. Modular assembly would help with this, as it would allow for easy assemblage, and easy transportation. And then these are slides. Because I have not finished.